Hello, friends. If you remember, back in 2014, director Christopher Nolan gave us a cinematic masterpiece, Interstellar. In this film, complex cosmic concepts like wormholes, black holes, and alien worlds were brought to life with staggering scientific accuracy. But perhaps the most shocking scene unfolds at the very end. During the ultimate climax, the main character, Cooper, plummets straight into a gargantuan black hole, falling deep into the abyss with his spacecraft. Initially, everything around him is pitch black, complete suffocating darkness. But as he sinks deeper, strange, grain-like cosmic particles begin to appear, violently striking his hull, scratching the metal. Then, flashes of light, sparks, and his spacecraft catches fire. Forced to eject, he continues his terrifying freefall into the unknown. And then, suddenly, he finds himself trapped inside a mind-bending five-dimensional space. 3D Tesseract, a reality where gravity allows him to cross time and communicate with his past self. Watching these scenes, you must have wondered, is any of this actually possible? Is this what truly waits inside a black hole? If a human fell into one, what would they actually see? Today, we unlock the ultimate truth. Welcome back. And if you love exploring the universe's greatest mysteries, make sure to support the channel by subscribing. Now, let's dive in.
Black holes remained largely unknown until the 20th century. A black hole is a region in space where the force of gravity is so strong, not even light can escape.
From the outside, you can't tell what is inside a black hole.
Black holes haunt our universe, dark centers of gravity that swallow everything in their path.
Let's start at the very beginning. The history of black holes is surprisingly fresh. Just a century ago, humanity had absolutely no clue these cosmic monsters existed. It wasn't until Albert Einstein introduced his revolutionary theory of relativity that the concept was born. Einstein's theory is split into two parts: the special theory of relativity and the general theory of relativity. In 1905, Einstein published the special theory, revealing a shocking truth: speed alters time. If you travel in a spaceship moving at near light speeds, time will drastically slow down for you. Compared to the people left behind on Earth, the word relative is key here, because while you are on that ship, you won't feel time slowing down at all. To you, seconds will tick away normally. But the moment you return to Earth, you'll realize you've traveled into the future. This mind-boggling phenomenon is called kinematic time dilation. But speed isn't the only thing that bends time. Gravity does it too. In 1915, Einstein released his general theory of relativity, proving that the stronger the gravitational force you experience, the slower time moves for you. This gravitational time dilation. And Interstellar captured this beautifully. Remember Miller's planet? The ocean world where just one single hour equals 7 long years back on Earth? That happened because the planet was orbiting dangerously close to the massive black hole, Gargantua. The extreme gravity was literally crushing time itself. To explain this, Einstein asked us to imagine space and time as a smooth fabric mesh. Every planet and star sits on this cosmic fabric. The heavier the object, the deeper it bends the fabric. And when the fabric warps, it doesn't just pull physical objects inward. It slows down time and bends energy itself, including sound, heat, and light. Yes, you heard that right. Gravity bends light. Einstein concluded that if an object in the universe became dense enough, its gravity would warp the fabric of space-time so severely that it would completely swallow light. If such an object existed, it would be utterly invisible, a dark bottomless void, because not even light could ever escape its jaws. And that is exactly what a black hole is. But back then, when Einstein first presented his equations, black holes were treated as mere science fiction. Pure mathematics. Einstein knew gravity could bend light, and theoretically, these light-eating traps were possible. But realistically, He never believed they actually existed in the wild universe. To him, the concept of infinity made sense on paper, but felt impossible in reality. In fact, by the time Einstein passed away, the very term black hole hadn't even been invented yet. And here is a fascinating fun fact. A core pillar of Einstein's theory is that gravity does not travel instantly. Its speed limit is the speed of light. Think about it this way. If the sun were to suddenly vanish right now, we wouldn't notice it on Earth until 8 minutes later. Why? Because it takes 8 minutes for sunlight to reach us. But according to Einstein, the gravitational pull would also take exactly 8 minutes to stop. For 8 minutes, Earth would keep orbiting an empty void. Incredible, isn't it? After Einstein, brilliant minds like Carl Schwarzschild, Johannes Droste, and Subramanian Chandrasekhar took up the mantle. They solved Einstein's complex equations and mathematically proved that black holes weren't just a glitch in the math. They were real. By the 1960s, the scientific community finally agreed. One day, we would actually find these monsters in deep space. The phrase black hole appeared in print for the first time in 1964, but it exploded into global popularity in 1967, thanks to physicist John Wheeler. But how do they form? While the name black hole sounds highly dramatic, it's actually a bit misleading. It makes you think there's a literal hole ripped into space. But that's not true. There is no hole. Black holes are the corpses of giant stars. Take our sun. At its core, a violent, continuous nuclear fusion reaction is always taking place, fusing hydrogen into helium. This reaction generates immense heat and outward pressure, pushing outwards. Meanwhile, the star's massive gravity pulls everything inwards. This creates a perfect cosmic balance, keeping the star alive and stable. But nuclear fuel doesn't last forever. Eventually, the fuel runs dry. The outward pressure stops, and with nothing left to fight back, the star's own brutal gravity wins, causing the entire star to collapse into itself. Now, don't panic. Our sun still has about 10 billion years of life left. But when a star does run out of fuel, its ultimate fate depends entirely on its mass. Look at the stellar life cycle chart. If a star is small or average-sized, it swells into a red giant, then sheds its outer layers to become a planetary nebula, leaving behind a fading core called a white dwarf. But if the star is a true titan, a supermassive giant, it cools into a red supergiant, and then it detonates in a colossal explosion called a supernova. What remains is a dense, dying core. If that core is relatively small, it compresses into a neutron star. But if the core is massive enough, it collapses indefinitely, shrinking down into a black hole. Think about the scale here. If our sun were to somehow compress into a black hole, its entire mass would be squeezed into a ball just 50 kilometers wide. Can you imagine that much matter packed into such a tiny space? But our sun will never become a black hole. This was famously proven by Indian-American astrophysicist Subramanian Chandrasekhar. He calculated the Chandrasekhar limit, proving that a dying star must be at least 1.4 times the mass of our sun to overcome atomic forces and collapse into a black hole. So, what do these cosmic beasts look like? Generally, they fall into 3 or 4 distinct categories. First are the stellar black holes. These are the standard ones, born from collapsing stars. Scientists estimate there could be anywhere from 10 million to 1 billion of these wandering inside our Milky Way alone. Second are the mysterious primordial black holes. These are purely hypothetical, ancient anomalies as tiny as a single atom, yet packing the mass of an entire mountain. We haven't found one yet. They remain a fascinating theory. Third are the true kings of the cosmos, supermassive black holes. These monsters are terrifyingly vast, containing the mass of millions, or even billions of suns combined, packed into a region no larger than our solar system. Astrophysicists now believe that at the absolute heart of almost every major galaxy lies a supermassive black hole. The one lurking at the center of our own Milky Way is named Sagittarius A and Gargantua. The iconic black hole from Interstellar was designed to simulate one of these exact supermassive giants. Scientists also suspect a fourth type exists, an intermediate black hole, bridging the gap between stellar and supermassive sizes. Though concrete proof remains elusive. Now, let's correct a major misconception. A black hole isn't just a giant dark sphere sucking everything up like a cosmic vacuum cleaner. In reality, they look like this. This render from Interstellar is incredibly accurate, providing a stunning 3D look at the physics involved. The first thing that grabs your attention is that blazing, glowing orange ring swirling around the darkness. This is the accretion disk, because the gravitational pull is so extreme. Massive amounts of gas, dust, and shattered planets are pulled toward the void, trapping them in a hyperspeed orbit. Just like planets orbit the sun, but on a chaotic scale. The material in the accretion disk spins so insanely fast that friction heats it up to millions of degrees Celsius. They literally become friction-ignited fire, glowing so intensely that they blast out electromagnetic radiation, mostly in the form of X-rays. Nolan's team got the physics of this disk perfectly right, with only one small stylistic tweak. It shouldn't actually be orange. Human eyes can't see X-rays, so scientists colorize it orange-yellow so we can visualize it. In reality, to a human observer, that disk would glow with a fierce, violent blue when the historic first-ever real image of a black hole was captured in 2019. Scientists used that same orange hue, but if you look closely at that real photo, you'll notice something strange. One side of the ring is significantly brighter than the other. Why? Because of an effect called Doppler beaming. The side spinning toward us appears compressed and bright, while the side spinning away from us looks faded and dim. By looking at the blur, you can actually tell which way the cosmic debris is rotating. Looking back at the movie image, notice how the glowing ring seems to wrap completely over the top and bottom of the black hole. That is a mind-bending optical illusion called gravitational lensing. Gravity is warping the light paths. The light from the disk behind the black hole is bent upward and downward by the extreme gravity, making it look like a halo from the front. If you looked at it from directly above, it would look like a perfectly flat normal ring, and right before you enter the abyss, you encounter the final ring of light, the photon sphere. Here, gravity is so intense that photons, the basic particles of light, are forced into a permanent orbit around the black hole. This means, theoretically, if you stood alive in this zone, the light reflecting off the back of your head would loop around the black hole and return to your eyes. You would literally see the back of your own head. Past this point lies the point of no return, the event horizon. This is the ultimate cosmic boundary. Beyond this line, the escape velocity exceeds the speed of light. If light itself can't break free, a human stands absolutely zero chance. You are officially trapped in Interstellar. Cooper crosses this event horizon and safely slides into a 5-dimensional realm. But let's be real, that part is pure science fiction. Because science has absolutely no idea what happens inside the event horizon. The filmmakers hired Nobel Prize-winning physicist Kip Thorne to keep the movie grounded in reality. But where science goes blind, Hollywood imagination takes over. What truly lies at the dead center? Einstein's equations call it the singularity, a single point where the curvature of space-time becomes infinite. Remember that fabric mesh from earlier? In a black hole, the heavy mass stretches that fabric into an infinite bottomless spike. And as gravity approaches infinity, time itself slows down infinitely. But what does infinite time dilation actually mean? If you fell into a black hole and somehow miraculously escaped, would you find that the entire outside universe had already ended? We simply don't know. We can only theorize. What do you think happens? Drop your theories in the comments below. One wild theory suggests that inside the event horizon, trapped light bounces around multiple points before hitting the singularity, meaning the inside might not be dark at all, but full of distorted, brilliant light. The only definitive proof we have is that historic photo captured on April 10th, 2019, proving that 100 years after Einstein drew it on a chalkboard, these monsters truly rule the dark corners of space. the brutal reality is. If you fell into a black hole, the tidal forces would rip your body apart molecule by molecule, a process physicists call spaghettification. You would disintegrate in milliseconds, but there is no need to fear black holes. People used to think they were cosmic vacuums that would eventually swallow the entire universe. But that's a myth. As long as you maintain a safe distance, you will orbit a black hole safely. Just like Earth orbits the sun, the universe is full of mysteries. And that fifth dimension concept from Interstellar, that deserves a video of its own. If you loved this cosmic journey, check out the other space videos on my channel. Don't forget to like, share, and subscribe. Thank you for all the incredible love. I'll see you in the next great video.